Hello everyone. This week, for a change, I did the biweekly contest number 40 instead of the weekly contest. And the reason I did that is because in Californian time it starts in the early morning and I was busy in the afternoon. We were in Tahoe, a great resort by the way, if you want to do some sledding or skiing or trail explorations, anything you want to do outdoors. Tahoe is a great place, great scenery, local cuisine is nice. People are a bit rude, but hey, no place is perfect. Great nature. Check it out during the winter. During the summer it's also fun. I've never been there during the summer, but I've heard it's nice. So much about Tahoe. Now back to the contest. My weekly contest number 40. I did record it from my car and I'll show you what this looks like. Test. Hey, good morning everyone. Starting in the early morning in Tahoe City. The conditions we're casting in are not perfect, but hey, we'll take what we can. Alright, going to leetcode.com and starting biweekly contest 40. As a matter of fact, it had started already 15 minutes ago, so we better hurry up. Let's do a before and after comparison. You've seen those pictures. And then before and after some amazing regime. Oh no, my battery thing. Okay, I have to run and get myself charging cable. I'll die here. My laptop will. Okay, battery life is 5%. We won't survive. We'll have to continue the recording from within the nice hut I'm staying at. And with that, all of our problems are solved. I'm not in real life, but hey. Now though, I wanna narrate post factum. I wanna narrate after it's over so that the explanations hopefully go a bit smoother and you hear a better analysis of the tasks given. First problem, maximum repeating substring. For a string sequence, string word is k repeating if word concatenated k times is a substring of sequence. The word's maximum k repeating value is the highest value k, where word is k repeating in sequence. If word is not a substring of sequence, word's maximum k repeating value is 0. Given strings sequence and word, return the maximum k repeating value of word in sequence. Just one moment. Here's what I was thinking while looking at the problem. The upper bound of the length of the sequence is very small, only 100 characters, same as the upper bound of the word we're searching for. The brute force solution is what I implemented and it works fine. You look for the word in the string. If you find it, great, it's there at least once. Then you add to that word the same word and you look for that concatenated substring. If it's in your string, great. If not, you return the answer. If it's in the string though, you continue, you append again the same word and again and again and again until you stop finding it in the substring. That solution is quadratic or so. In complexity it's not elegant at all, but it works fine. You have concatenations. I didn't even use the string builder. You have multiple calls to index of. These are all expensive, but that's fine. For this small size of our problem space, that's completely fine. Now, there could be potentially some smarter way to do it as a binary search, starting with the string mid-size, and then if you find it, you try with a longer one. And if you don't find it, you try with a smaller one. And so you binary search within the space. Let's take a look at the discussion section and see if that's even an option there. Brute force. Oh, there you go, you have KMP. For those who don't know KMP, that's Knut Morris Pratt. It's a classical string search algorithm, not too complicated for the limits of this competition. But you can find information on it on the internet. I think it's useful to learn it. Yeah, maybe there are some other ways to find it, like you could optimize and look for the number of characters initially to see if it makes sense. Even to search for a certain length words, you can limit your search space. I wouldn't. You could find a myriad of solutions. Again, straightforward problem. Okay, problem number 2, merge in between linked lists. You're given two linked lists, list 1 and list 2 of sizes n and m respectively. Remove list 1's nodes from the 8th to the bth node and put list 2 in their place. The blue edges and nodes in the following figure indicate the result. What we're doing here is we're subtracting this piece, cutting it off from node A to node B, and in its place we're putting the entire list 2. This solution was straightforward. You do exactly what is explained here. The tricky part was making sure that you're correctly having all the pointers pointing to the correct nodes. So if we look at my solution, what I did was I preserved the original head because this is what we want to return, a pointer to the original head of list 1. Second, I found the tail of list B, which is this m-1 node here. I iterate over the whole list 2 and get that tail. I also need several other pointers. I need this node here, a-1, and this node right here, b+1. This is what insertion start and insertion end were. So I called a-1 insertion start and b+1 insertion end. And I needed those so that I can attach together the lists correctly. I just iterated over list 1 and first kept this guy, then continued iteration with the same pointer, going through the red space and reaching b+1, and kept that as well. And after all this was done, right here at the end of it, I just glued together a-1 to 0 element of list 2, which is just my list 2 input parameter, and then m-1, which is list 2 tail, points to insertion end, which is b+1 in this graphic here. And that was all there was to it. In the end, I just returned the beginning of this list 1. Easy peasy, lemon squeezy. Third problem. Design front, middle, back queue. Design a queue that supports push and pop operations in the front, middle, and back. Implement the front, middle, back class. And you have initializer, you have push front, push middle, and push back methods. You have pop front, pop middle, and pop back. You have to return -1 when the queue is empty. And there was an important rule here that if there are two possible positions at which you can insert in the middle, you need to take the frontal one, the one closer to the start of the array. In this example, 1, 2, 3, 4, 5, if we put 6 in the middle, it would come in before 3, not after 3. And same with popping. If you're popping from the middle, you're popping 3, not 4 in this example here. These are important rules. The way I implemented this was with two queues using the DQ interface in Java. Implementation of it is a linked list, doubly linked list, which allows you to insert in the beginning and in the end. The idea here was I would have those two queues, and the end of the first one and the beginning of the second one would be my middle elements. And so whenever I'm inserting, doesn't matter at the end or in the middle or at the beginning, either way, I would be rebalancing my two queues, trying to keep around the same amount of elements in both, meaning the maximum difference of size between the two queues would be just 1. So this can be 3 and this can be 4 elements, or this can be 5 and this can be 4, or they can be equal. There would never be a gap of more than 1 in their sizes. With this rebalancing operation, I've called this private method here rebalance, that I execute after every action, literally. I guarantee myself that this pop middle, which is the complex operation, right? It's unusual. Everything else you have in the standard queue. Pop middle is in constant time. The rebalancing, just because I'm at most shifting one element to rebalance, 0 or 1, is not adding to the complexity. It's a constant operation on every push or pop. I called my first queue A and my second queue B. I assumed if the elements are not equally distributed between first and second queue, then the bigger queue would be B. I'll never have a case in which A would have more elements than B after rebalancing. And this is what happens. When you push to the front, you add an element at the beginning of A, and then you rebalance. When you push to the middle, you add element to the beginning of B, which is somewhere in the middle, right? And then you rebalance again. When you push at the end, push back, you add element to the end of B, and you rebalance. Maybe I'll go right now through the rebalancing operation so you understand what does it exactly do. It's no magic. It would look at the sizes of A and B queues. If A is too small, 2 elements smaller than B, we would shift one element from B to A. And if it's the other way around and A is too big, then we would shift an element from A to B. So we offer to B the last element of A. That's really it. If one of the two queues becomes too big, we shift the last element of the first one as the first element of the second, or the other way around. We shift these middle elements so that we have this roughly equal amount of elements in both queues. Pop front removes, and here was the tricky part. It would usually take the first element of A, but because we have sometimes the case in which we would have 0 elements in A and 1 element in B, we would have this additional else clause where we would remove the element from B. And then pop middle does exactly the same. If the size of B is bigger, it would remove from B, else it would remove from A. Again, rebalance at the end of that operation. Pop back would do the same. And there's again is there an edge case though here? Let's see. Okay, there is no edge case. And this is something I could remove safely, just because I'll keep B the larger of the two parts. And that's it. You have the operations, they work exactly as you would think they would, with the caveat that after every one of them, you have a rebalancing action, which is keeping the two queues same in size. And this was my implementation of the front, middle, back queue. Coolio. Last problem is the hard one. Last but not least, we have the minimum number of removals to make mount an array. You may recall that an array R is a mountain array if and only if R length is more than or equal to 3, and there exists some index I such that all elements from 0 to I are steadily increasing and all elements from I to the end of the array are steadily decreasing. Given an array nums, return the minimum number of elements to remove to make nums a mountain array. It's qualified as hard, and if you've never seen a problem like that, I agree with that, it's hard. However, this is very, very close problem to a textbook dynamic programming problem, longest increasing subsequence. And you'll see what I mean in a second. Why is this problem easy? Because you can break it into two subproblems. Find the longest increasing subsequences from the beginning of the array to the top of the mountain, and then the longest increasing subsequences going the other way from the end to the mountain top. And once you find for every element what's the longest subsequence going up from the beginning to it, and the longest subsequence of elements decreasing from it to the end, and you sum those two, you will get the correct result. For those not familiar with longest increasing subsequence problem, perhaps that's something more interesting to look at. It's available on Wikipedia and on a bunch of other sources. And there are multiple solutions to it. The very simple quadratic dynamic programming solution is find the longest subsequence to every element before my current element I, and then see for I if any of those elements plus I wouldn't make a longer and better subsequence. This happens like so. This is I, and then this is my second loop, so the solution is quadratic. For every I, go through all elements before I, for which we've already found the longest increasing subsequence. And if this previous element j is smaller than I, which means it satisfies the condition to be part of a continuously increasing subsequence, strongly increasing, then see if the longest increasing subsequence that was ending at j plus this new element, which is increasing the length by 1, is better than what we have currently for I. And if it is, then store the new maximum. So try this for every previous j, which satisfies this condition right here. And by the way, this is badly formatted. Unless I add curly braces, it should be on the same line. Style. Yeah, so that's it. Keep going through all previous elements and see if you have a better longest subsequence for I. Then do that for the next I and so on. You do that in reverse for the second part of the mountain, the downward slope. You make it increasing subsequence by starting from the end of the array and moving to the front. You also, on your way back, since on the initial run you found the local maximum coming forward, now you have the maximum going backward, summing the two and adding one for the actual mountain top, which is not part of the sequence, the way I've implemented it. You can check if that is the best possible, the longest possible mountain array. Once you go through all elements, you will have eventually the longest mountain array, combining the biggest sum of forward going longest increasing subsequence and backwards going longest increasing subsequence. And then at the end, because you're looking for the number of elements to remove to make nums a mountain array, you return n minus the length of the best mountain array or longest mountain array. Maybe this should have been called longest mountain array. Yeah. And this was the last problem to solve. I solved all problems in 1 hour and 20 minutes, which is not great. And considering they were relatively easy, I have a few lame excuses, like I was coding in my car and then my battery died. I had to move to our hut in the forest and reconnect all my equipment. And then I was also narrating a narration which I end up now, I guess, throwing away. As I said, lame excuses, but anyways, the good thing is I solved them. I had a bug in the last problem, and the bug was I wasn't careful to notice that you cannot start or end your solution on a mountaintop. In other words, you cannot have only a downward slope or only an upward slope. You need to have both. Your mountaintop cannot be in the corners of the array, and that's an edge case I didn't take care of initially. So therefore, I had one buggy solution here. Without this check right here, you don't exclude those edge case arrays that have only downward or upward slope. And then a cliff at the end of the array. Not a mountain by definition, I guess. And as is traditional, let's take a look at which company asked which problem. The first problem, maximum repeating substrings, was asked by Asana. The merging between linked lists problem was asked by Sambanova. Amazon asked the design front middle back queue. And Microsoft asked the minimum number of removals to make mountain array. There you have it. A bit shorter and a bit sweeter, hopefully. Next time, maybe I'll have more time. Bim bam boom, we made it. I don't know. What could I have done better? Should I have solved the problems in a different way? Think about it. Maybe let me know. Write down in the comments. anything, any thoughts, share with me. And thank you for your time. I'll see you again. One thing I wanted to say is alright, that was it. And see you next time.